Hello guys, this is a video solution for the problem sheet for week 10. There are 3 questions in this problem sheet, and I will go through every one of them and give you a detailed solution. So please note that this video solution is on top of the typed solution and the handwritten solutions, both of which you can find on the course website. Question 1. You are given the following joint CDF. Right? And for x greater than 0 and y greater than 0. Now part A is asking you to show that this is a bivariate extreme value distribution. You may recall that I gave you 4 representations for a bivariate extreme value CDF. So what you need to figure out is which of the 4 representations this falls under. Alright? Now to do that, the first thing you must try to do is to determine the marginals of this. So to find the marginals, you put x equal to 0 first. So if you put x equal to 0 into this, right, you will get e of minus y. It's not difficult to see that. And if you put y equal to 0 into this, right, you get this. And as you can see, both these are exponential marginals with parameter 1. Right? Hence, the representation that you're looking for is the representation number 4. Right? So in other words, you need to express G bar here. You need to express G bar in the following form. Right. Okay, for a function A. So we need to first of all determine this function A corresponding to this, right? All right. So this is the representation that you. Okay, let me put this in. This is basically representation 4, right? Okay. So to determine that function A, first of all, I'm going to go back to what is given here. Okay, and I'm going to rewrite this as follows. I'm going to pull out x plus y outside, right? Then in brackets you will have the following. Right, so your function A of this is basically this, right? So this implies that the function A, let's say W or omega, whichever way you want to call, must be equal to theta W squared minus theta W plus 1. right? So in order to show that this is a bivariate extreme value distribution, we must show that this function satisfies the conditions that I listed in the video on bivariate extreme value distributions. So the first condition, you may recall, there are 4 conditions. The first condition is that a of 0 must be 1. The second condition, you may recall, is that a of 1 must be 1. The third condition, you may recall, is all right, for all w. And the fourth condition, you may recall, is that a must be a convex function. So what remains to be done is to show that this function satisfies each of these conditions, right? So let's start with condition 1. Clearly, a at 0 is equal to theta times 0 squared minus theta times 0 plus 1, which is equal to 1. So hence it is satisfied. 2. Condition 2, a at 1 is theta times 1 squared minus theta times 1 plus 1 is equal to 1. So hence it is satisfied. Okay. Now condition 3, right? Let me check. Okay, let's see how we can address condition 3. Condition 3 is basically, okay, let me write it down here. Condition 3 is that the max w1 minus w must be less than equal to a of w, must be less than equal to 1 for all w. Now, this is the same as saying the following, that a of w must be less than equal to 1 for all w, a of w must be greater than equal to w for all w, and a of w must be greater than equal to 1 minus w for all w. So we need to show each of these things, right, in order to show this. So let me call this, say, let me call this alpha, let me call this beta, let me call this gamma, right? So I want to show each of these. So starting with alpha. So a of w less than equal to 1 for all w, right, is the same as wanting to show that plus 1. Okay. Now, sorry, less than equal to 1. Okay, the 1 and the 1 cancel, so this is the same as saying that right. Okay, now this you can write as this, and this is always not less than equal to 0, because w, as you know, is a number between 0 and 1, right? So w minus 1 is always less than equal to 0. Theta is a positive number, w is a positive, non-negative number, so this is always true, right? Now, beta, we need to show that okay, which is the same as okay, and this is the same as right, and this is the same as 1 minus theta w, and this is true. This is also true because I don't know whether I said in the question that theta must be a number between 0 and 1. Okay, so that means 1 minus theta omega or theta w must be non-negative, right, if theta is between this and this. And 1 minus w is also non-negative, right, so the product must be non-negative, right. And gamma, we need to show that okay, which is the same as wanting to show okay, the 1 and the 1 cancels. Alright, so this becomes theta omega squared or w squared plus w times 1 minus theta greater than or equal to 0. Alright, and this is true once again because theta w squared is non-negative, right? And theta times 1 minus theta is also non-negative because, as I said a minute ago, we are assuming that theta is a number between 0 and 1. All right, so 1 minus theta is non-negative, so and this will be non-negative too. So we have proved, going back here, so we have proved the 3 conditions, that A alpha, beta, and gamma. Right? So we have proved part 3, condition 3. So the condition 4 that remains to be shown is the following, that we need to show that A is a convex function. Now you may recall from the video I did on bivariate extreme value distribution that to show that something is a convex function, right, you need to find the second order derivative. Now we know that A of w is theta w squared minus theta w plus 1, right? So the first order derivative is 2 theta w minus theta, and the second order derivative is 2 theta, which is positive. So hence A, the function A, is convex. Right. All right. So hence we have shown that hence G or G bar corresponds okay. So we have proved part A of question 1. Now the 6 remaining parts are pretty routine, so I will just briefly show you what to do. For part B is asking you for the joint CDF. So the joint CDF, which I shall denote by this, right, can be obtained from the joint survival function as follows. So I did a video on this some time ago, so you should look at that video. This is a relationship between a joint CDF and a joint survival function. So you use this use this relationship to get the joint CDF from the joint survival function. That's part B. Now part C is asking you to find the conditional CDF of y given x. So this is the conditional CDF of y given x equal to x, and this is given by the following formula. The formula for that is simply this. So what you have to do is just find the partial derivative of the joint CDF with respect to x, and then divide by this. All right, this is the formula you need to apply to find this, right? And part D is asking you to find the conditional CDF of x given y. All right, so to find this, use this formula. So you find the partial derivative of the joint CDF with respect to y, and then divide by e of minus y. All right, that's part D. Part E is asking you to find the joint PDF. The joint PDF is simply the second order partial derivative of the joint CDF, which is this. All right, so use this formula. And part F, to do part F, you simply divide what you got here, right, by, so let me call this, say, just for notation, let me call this little g, right? Right, so to do part F, you simply divide the joint PDF by this. So this will give you what is asked for in part F, which is the conditional PDF of y given x equal to x, right? And finally part G. To do part G, you will do this. You will use this formula. So you will divide the joint PDF by EF minus y. So this will give you the conditional PDF of x given. Okay, so this completes question 1 of sheet 12, right? And so let's move to question 2 now. So let me show you. This is question 2. Here you're given that G bar is equal to this, right? All right. So the first thing you must try to do is to find the marginals, right? Marginals of G bar, right? So you put first x equal to 0, and this will give you E of minus y, and then you put y equal to 0, this will give you e minus x. So which means that the marginals right. So once again we need to use the representation 4 I talked about on the video on extreme value or bivariate extreme value distribution, right? So the first thing to do is to write G bar, right, in the form of representation 4, right? So that's what I'm going to do now. I'm going to write this by pulling out this, okay, and if you pull this out, you get minus of alpha xy divided by x plus y squared, then plus 1. Right. Okay, so this guy here inside the square brackets is your a function. So what this implies is that your a function is equal to minus of okay, so which implies that your a of w, right, is equal to minus alpha w 1 minus w plus 1. Okay. All right, now what we need to show is the 4 conditions. We need to show that this function satisfies the 4 conditions, which so the first condition is that a of 0 must be 1. Condition number 2 is that a of 1 must be equal to 1. And the third condition is that all right, and the condition 4 is that a must be a convex function. All right, so let's start with condition 1. So to do condition 1, you just put w equal to 0, so which clearly implies is 1. So that is satisfied. Condition 2, you put w equal to 1. Again is equal to 1, so satisfied. So condition 3, as I said in the previous question, to show this we need to show 3 things, right? So this is equivalent to showing that a of w is less than or equal to 1 for all w. Let me call this let me call this, say, we are already using beta, right? Let me call this gamma. A of w must be greater than or equal to w for all w. And let me call this delta. A of w greater than or equal to 1 minus w for all w. So we need to show each of these things, okay? So let's start with beta, then gamma, and then delta. Which is the same as saying that the 1 and the 1 cancel. right? And this is always true because W is a number between 0 and 1. 1 minus W is also a number between 0 and 1, and alpha is a positive number. We are assuming that alpha is a positive number, all right? All right, now next, gamma. Okay, so this is the same as saying all right, and this is the same as saying that 1 minus W in brackets 1 minus alpha now this is true once again because we have to assume that alpha is a number between 0 and 1. Okay, so if alpha is between 0 and 1, then 1 minus alpha W will be a non-negative number, and 1 minus W will also be non-negative, so the product will be non-negative, right? Okay, now simplifying this is what you will get. And this is once again true because we must assume that alpha is once again between 0 and 1. So 1 minus alpha times 1 minus W will be a non-negative number if this is true, right? Okay, so all three, so the beta, gamma, and delta, all conditions fall. So condition 3 is satisfied. So the only remaining condition that we need to check is condition 4, which is that A must be a convex function. We know that A is alpha 1 minus alpha W times this. So the first derivative with respect to W will be minus alpha plus 2 alpha W. Okay, and the second order derivative is 2 alpha, and this is positive, right? Hence A is convex. All right, hence G bar corresponds to a bivariate okay. So all right, so we have shown that the first part of the question, that is to show that G bar corresponds to the bivariate extreme value distribution. Right, now the remaining parts of question 2 are the same as what I just mentioned in question 1, right? So this is part A. So to do the remaining parts, so to do part B, which is asking you for the joint CDF G. Right, so to do this, you use the following relationship, which I mentioned in one of the previous videos. So this is part B. To do part C, which is asking you to find the conditional CDF of y given x equal to x, right? And this will be given by the following formula. Right. Part D, to find the conditional CDF of x given this, you will use the following formula. All right. And to do part E, which is asking you for the joint PDF, you will use the following. So it will be the double derivative of the joint CDF with respect to x and y. So let me call this little gxy, okay? And to do part F, which is asking you for the conditional PDF of y given x equal to x, right? To find this, you okay. And finally, to do part G, to find this, you use the following formula. All right, so this completes question 2 on sheet 12. In question 3, we have g bar x comma y equal to this. Right. Okay. Now we need to show that this is the first part is to show that this is an extreme value, bivariate extreme value distribution. Now I gave you 4 representations, you may recall. So we need to determine which of the 4 representations this falls under. So to do that, the first thing you need to do is to find the marginals. So to find the marginals, you put x equal to y, and also, you put x equal to 0 and y equal to 0. And if you do that, you will get this for the first, and you get this for the second. And these are clearly exponential marginals. So what that tells you is that we need to show that this takes the form of the representation 4. So we need to use representation 4. Alright, so we should try to write the form for G bar into something that looks like the form under representation 4. So that's what I will do now. I'm going to write this as follows. Okay. Right. Now, if according to representation 4, this must take the following form. Right? Okay. So what this tells you is that your the function a must be, if this is the same as this, a must be this, right? Okay, this is your function a of w or a of omega, whichever way you want to call it is okay. Okay, now we need to show that this function the function a satisfies the following conditions. There are 4 conditions you may recall. The first is that a at 0 must be 1. The second is that a at 1 must be 1. The third is that right, and the fourth condition is that a must be convex. Okay, let's try to show one at a time. All right, starting with condition 1, which is a of 0, which is equal to 1 minus 0 power a, 0 power a to the power this, which is clearly equal to 1. So condition 1 is satisfied. Okay. Condition 2 is that a at 1, which is right. So this is 0, this is 1, so you get 1 again. Okay, and condition 3, now to show condition 3 I need to do 3 things, right? Condition 3 is equivalent to the following, that a of w is less than or equal to 1 for all w, a of w is greater than or equal to w for all w, and a of w is greater than or equal to 1 minus w for all w. All right, so we need to show each of these. So let me call this, say, alpha, beta, and gamma. Okay, so I will show each of the conditions alpha, beta, and gamma. All right, starting with alpha. Now, we know that w, right, is less than or equal to 1, right? I mean, by definition, right? It's a number between 0 and 1. So w power a should also be, it should be less than or equal to W, right? That's because we are assuming that, okay, I should have said this before, but we are assuming that A is a real number that is greater than 1. Otherwise you can't do this. You cannot do this question, right? It also implies that because 1 minus W is also a number between 0 and 1, 1 minus W power A is also less than or equal to this. That's because of the same thing, right? Now summing these two, you sum these inequalities, you get W power A plus 1 minus W power A is less than or equal to W plus 1 minus W, which is equal to 1, right? And this implies that, okay, that W power A to the power 1 over A, if this is less than or equal to 1, then this power, this must also be less than or equal to 1. So hence we have shown that A of W is less than or equal to 1 for all W, right? So that's condition alpha, right? Condition beta is the following. We need to show that A of W is greater than or equal to W for all W, right? Which is the same as saying that okay, and this is the same as if you take the power, both sides, power to A, okay, now these two cancel out, okay, these two cancel out, so what you have is like this, and this inequality always holds. Okay, so hence we have shown condition beta. Right, similarly you can show condition gamma as follows. Okay, now take the power both sides, you get this, all right, and these two cancel out one more time, all right, these two guys cancel out, so you get W to the power A greater than or equal to 0 for all W, right? Which is always true. All right, so hence we have shown condition 3 holds, because condition alpha holds, condition beta holds, and condition gamma holds. So the final condition that we need to show is condition 4, right? Which is that A is a convex function. Remember, to show that something is a convex function, you need to show that the second derivative is positive. So let's see how we can do that. We know that this is the A function. Alright, so we need to find the second order derivative. So let's find the first order derivative, right, which is going to be 1 over a right, and multiplied by the derivative of this, which is okay. Now you should simplify this. This is, you will get the a cancels out, so you get w power a minus 1 minus 1 minus w power a minus 1. So this is the first order derivative. Now we need to find the second order derivative, so which is the derivative of this. So we need to use the product rule. Right, so this gonna be multiplied by the derivative of this, right, which is let me write it over here. It's gonna be right. So that's only one part of the product rule. The second part of the product rule is gonna be this. Right, times the derivative of this, which is a minus 1 times w a minus 2 plus, okay. All right, now we need to simplify this and ensure that it's positive, right? You should do that. All right, actually, all right, let me show you. Okay, you should combine these two terms. 1 over a minus 1 multiplied by a gives you a minus 1, right? Okay, then you have these two terms which have a common factor. You can pull that outside, so it's going to be this. This is going to be the common factor, right? And so inside the brackets, you're going to have the following. You're going to have this, right? This part of this we already pulled out, so it's going to be plus right? I hope you follow what I'm doing. Times this times this, right? So it's going to be times all right. So this is the simplified form of the second order derivative. Now this is actually positive because this guy here, we are assuming that a is a number greater than 1, as I said before. So this has to be greater than 0. And W is a number between 0 and 1. So this has to be greater than 0. And what you have here is to the power 2. So anything power to 2, anything must be non-negative. And here you have W, which is a number between 0 and 1, so this has to be greater than 0. Right? And also here, W is a number between 0 and 1, so this has to be greater than 0. So hence, we have shown that this is greater than 0 for all W. So hence, we have proved all 4 conditions that must be satisfied by the function A, right? So hence, the conclusion is that G bar corresponds to A bivariate extreme value distribution. Okay. So this completes part A of question 3. The remaining parts are I'm not going to work them out, but I'm sure you know how to do them because I gave you the formulas, just like in the previous 2 parts. So for example, for part B, what you need to do is to find the joint. The question is to find the joint CDF, right, which is G of x comma y. So to find this, you use the following relationship. All right. So this is a relationship I gave you a long time ago, you may recall. For part C is to find the conditional CDF of y given x equals to x. And to find this, you will use the following formula. You will use 1 divided by e minus x times the partial derivative of the joint CDF with respect to x. Part D is to find the conditional CDF of x given y equal to y, and to find this you will use the following formula. Okay, and to part E, the question is to find the joint PDF. All right, and you will use the following. So it's the second order partial derivative with respect to x and y of g of x comma y, which I shall denote by little g x comma y. This is just a notation. And part F is to find the conditional PDF of y given x equal to x. Right, for this you will just simply use the formula that g of x comma y divided by e. Right, so this is the formula for the conditional PDF of y given x. Right, and finally part G is to find the conditional PDF. Okay, and find this, you will use the following formula. All right, so this completes question 3.